Every LLM project goes through the same way. A promising prototype, a few impressive outputs, and also excitement what is possible. But when you put the prototype in front of the user, reality hits. You would face unpredictable output, edge cases, silent failure, and a hallucination that looks confident, but literally it breaks the downstream systems. And that's exactly where my stage 4 of the roadmap, which is called quality and reliability, can come here to help you to stop hoping that the model would behave very well, but you engineer the reliability layer of your own application by yourself. In this video, we are going through the 4 principles of this stage together that turn the fragile behavior of LLM model to dependable performance. The topics are hallucination mitigation, human in the loop, structure output enforcement, and error handling fallback strategies. We are not covering only the tricks, but also the mentality that you can literally use it cross over multiple LLM applications, plus hands inside the coding by yourself. If you would like that your LLM products survive in real-world pressure, that's exactly the transformation is happening. Let's go through all the topics together. Have you tried ask questions from AI system and you got the answer which looks perfect, but you will find out it's completely wrong? Well, it's not just annoying. In legal, financial, medical, or enterprise setting, this can be quite dangerous. In this video, I'm going to talk about one of the biggest challenges of LLM-based applications or AI systems, which is called hallucination. And I'm going to address 3 concrete approaches to help you mitigate hallucination in your applications. Stay tuned with me. Well, let's start with a clear, simple definition. When we are saying a model hallucinate, it refers to the moment that the model is generating the output, which is factually incorrect, inconsistent in logic, unsupported by provided context, or just completely invented. We need to understand that the model doesn't try to lie to us in human sense or even deceive us. It is just predicting the most predictable token based on whatever data it got trained on. Well, when it doesn't have the proper context or information or enough confidence, it just tries to fill the gap based on what looks plausible to it. And that would be quite dangerous in some domains, such as legal reasoning, scientific explanation, financial analysis, medical information, or enterprise knowledge system. In these domains, just being confident is not enough, but the answer in such systems should be quite grounded. And that's why mitigating hallucination becomes super important. In my previous video, I talked about prompt engineering and context engineering, which can help us for sure. If you don't know about them, please go back to my previous video and see what are the kind of techniques there. But in this video, I'm going to talk about additional 3 approaches. Let's go through them one by one together. The first approach is retrieval augmented generation, or RAG in abbreviation. You probably heard of it because it's one of the most well-known approaches. RAG system works literally when you are providing external information for your model when it needs it. Then your model doesn't need to rely completely on the data it got trained on, but it will pull in information when it needed from APIs, knowledge bases, databases, and doc stores. It makes your system quite powerful, because the system will not rely on the training data on your LLM model, but it is tied to actual information you're providing. But you may face the question, what changes it bring? Really great question. For sure, it will drop hallucination sharply, because as I mentioned, it will refer to detailed information, relevant document you're providing for your LLM model. and the model is not inventing any information by itself. The second advantage is about freshness of the retrieved information, because you can continuously update your external information. And even the training data in your LLM model gets old, always you have access to up-to-date information. And the third advantage is about domain specificity. You can tailor your RAG system on specific domains of legal, medical, or internal enterprise information. And the advantage is that whenever any questions relevant to these domains pops up, your RAG system retrieves quiet, relevant, grounded information. You can see clearly the advantage is huge. And if you want to build any reliable, scalable information, then that's for sure one of the solutions you should come and try it. If you're going to build any type of question answering or retrieval information that relies on facts and grounded information, RAG for sure is the first tool you need to think of it. If you don't know about RAG is the third stage of my roadmap that I covered it so far. The handbook of it is ready in my website. You can get the information about how to design a pipeline of the RAG, what are the components in this pipeline, and build your RAG system from bottom up. The second approach is tool use, or more broadly protocols such as MCP or Model Context Protocol. The idea is quiet, simple, and still powerful. Instead of forcing your model to just rely on its internal patterns to answer any type of the question, you give the model the ability to just find the tools that can provide information for you. It can be pulling information from databases. It can be calling search APIs to look for something up somewhere else, or even calling internal APIs for grounded information, or even calling any dedicated mathematical tool for precise calculation. All of these actions replaces uncertainty with verified result, and you can literally get the point why it is important. It is important when numbers, up-to-date information, structured data, and verification is important for you. In these cases, using the tool call, the model doesn't invent anything by itself, but just get relevant information when it's needed and where to call. Protocols such as MCP or other cases, they just standardize this pattern. That when I need information from outside, what are the tools I can use when I call them already, how to integrate back their answer to the conversation that I had before. It's quite simple. Retrieval augmented generation is talking about retrieve information, but tool use is more about just calling which tool and when and how to integrate back. And they are following the same logic for LLMs that don't rely only on the memory you have. Let's try to find out the information somewhere else. Well, you got to know how to mitigate the hallucination with different approaches. One of them was MCP and tool use. That's exactly this example that I'm sharing in the screen with you, and I'm gonna go through the code together with you. This MCP that I implemented is for an LLM-based application with 4 tools that gonna navigate the user queries to different tools. But how is it working? The code is quite simple, and when you get the handbook, you can get different guidances. Simply, the very simple first one is about the Python libraries you need to install, that you can find it in the requirement. Then about the MCP server that I install, I'm using the MCP Python library in the requirement. It has 4 tools in my code that we will go through the different tools together. The very first tool of the MCP that has this decorator you can see here is about getting customer subscription. So assuming that in our LLM based application we have list of the customers, and anytime the query comes from the user, that the user asks about specific customer. And this is exactly this type of the tool that can handle it. It gets the customer ID and it searches in the database to find the information about that specific customer. If I just go down, I use SQLite, and that specific customer ID will be given as a parameter to this database SQL query, and it will fetch the output, and at the end it will give it as one row with the information of that specific customer. For this specific case, we need to have database of the customers. So to simplify your running, what I did, there is a CDB Python code. In this Python code, you need just to import the SQLite and create a one.appDataDB, which I already have it here. If you don't have it when you are running this code, it will create that table for you about the customers inside of that database, and it will add some of the rows about different customers. These are just the sample cases of the customers, and insert them one by one into the database. And at the end, you would have, after running this code, you would have this one.appDataDB in your code. Going back to the MCP server, we were talking about the first tool, get customer subscription, that it will connect to that specific database we created with the CDB code, and it will give this specific customer ID to the SQL code and pass it to the DB. And at the end, it will get the output about that specific customer, give it as an output. That's one of the tools that I implemented in this MCP. Another one is about the policies. So anytime the users come with a question about the policy, either it's about refund, security, SLA, then it will go through the text of the policies that I prepared here on the top. You can see different policies. For instance, our application has about the refund, security, and SLA. And anytime the user has any question about these specific policies, then this tool is assumed to be called, and then look inside of the data information about policies and give the output, that whether it could find it or not, and what is the text information. The other tool inside of the MCP is about calculation. For instance, the user does ask any arithmetic question by using their natural language query, and it will go through different steps to just calculate any arithmetic request from the user. At first, it will call the evaluation function, which checks if it is inside of the, let's go through the function together. So inside of this function, it will check about the question that the user asks in their own natural language. It will check that if there is any digits or float information inside of the code or not, whether the request from the user is operations inside of or allowed type of the operation or not. For instance, on the top, I listed the allowed type of the operations that the user can request, like add, subscription, multiplication, or positive or negative. And other than that, for sure, we will check to not run them. And with this drilling down the scope of the application, we can mitigate hallucination that the LLM model itself doesn't generate or invent any text that we don't want. Well, I mentioned about the third tool, and the last one is that, for instance, the user asks any question about if specific customer is eligible to get refund or not. And for this specific request, when any specific customer is given, again it will go to the database, search for that specific customer, and when it search about it, it will extract what kind of the plan subscription the user has, and it will check whether these type of specific plans that the user has are inside of a refundable or non-refundable type of the plans, and also if the user is active or not, or maybe within the 30 days they ask for the refund, which is the value of the refund window policy. All of these parameters I also set them in the top. So only refundable plans are Pro and Enterprise, and non-refundable is just a starter ones that they are on monthly basis get the subscription. And if the user asks any refund within the 30 days after the payment, then also this will be checked. So simply I explained 4 different tools that I implemented in the MCP server. Well, now that I implemented these 4 tools inside of the MCP server, we have a simple agent that any request comes from the user, it will pass it to the MCP and make a session with it. In the code, I just give a sample question if specific customer is eligible for refund, and also I added a arithmetic request to the agent and see how it would get the response. Well, it will try to answer the query with function of answer with MCP. Inside of this function of answer with MCP, it will at first get the open AI API credentials that I have to check that we have any type of the credential or not, and what is the model, get the default model. The default model that I'm using is GPT-5 for mini. Going back to the code, when you check about the credential part, then it will connect with that MCP server and consider it as a server to create the stream of the read and write with it. Inside of the MCP server, when it connects with it, it lists all of the tools that it has and shape them inside of the API tools, like with this type of a structure, that what is the type, it is function, the name, description and parameters of it, and set these values, because later it cannot send it to LLM model as input. Then it will go through 6 rounds of the multi-turn tool loop to check that it can get the result or not. And how is it working? It has the message list of the queries that come from the user, and also the list of the tools of the MCP that they are structured, I showed you on top, and give it to the LLM model. And during this time that is connected to the LLM model, we get also some we get the tool calls from the output of the LLM model. And if there is a tool call, the LLM model can recognize whether there is a tool call or not after the connection with the MCP, and it will list them, the output of the content of the output of the LLM model in the content, and attach it to the messages that we gonna use it later. I will explain it how is it useful. So the output of the LLM model will be given inside of the content, and all of the tool calls, if exist, they will be listed inside of the tool calls of the messages. So we want to be sure that if LLM could recognize very well which tool should be called. That's the point of adding these specific tool calls in the output of the LLM model. So if any tool call was in the output of the LLM model, then it will call through a session that already open with the read and write with LLM model, and give that a specific function of the name to call that specific tool, and when all the arguments are given also to the tool call, it will call a specific function that is already passed, and the output of it will be delivered as tool result. So every time, as I mentioned, it will go through different tool calls. If there is any tool call that is recognized, it will call the corresponding function of it, and it will pass the information to that specific tool and then get the result at the end. So we have the result of the tools at the end, that they will be inside of the tool result text. Those functions that are called and what the output of them is there is inside of tool trace in the output, that when we are generating the output, and that's exactly helpful that we can trace what kind of tool is called inside of our code. And at the end, it called the function of the bill run report. The bill run report here, the function is quite simple. This function at the end generate the output inside of the markdown output file. So anytime you are running the code, I already run it before, it gives you this output. This output is just for clarification for you, to show you what's going on in the backside of the code. For instance, here it shows that when I run the model and which model I use and what was the query that I ran it. During the connection with the MCP, it will list the MCP tools. So you can see already we have 4 MCP tools, but not all of them are called. So in the tool call trace that I showed you inside of the agent code, it could recognize very well to at first call the tool of refund eligibility of the specific customer. So it at first pass this specific customer that is in the user query. You can see here it will pass it to this specific tool, and the output of it as a JSON would come like this. And you can see the plan of this specific customer is pro, so it will give the reasoning that this specific customer meets all of the refundable plan, and he is eligible to get the refund at the end. So that's for one of the tool call trace that correctly could call the correct tool. Let's go to the second one. Second one was arithmetic, and we expect that the calculation tool to be called. So this part of the query is given as an input, and at the end it is checking whether they are digits, what kind of operation is it, which is the multiplication. So it passes all of the checkpoints, which is okay to go with the calculation, and it will create this output for us. So you can see that it is correctly called the 2 functions, and the output is also correct. We mitigated the hallucination to avoid that the LLM model generate random output by itself, but we routed the LLM to go to specific tools and do a specific functionalities. And at the end, the final answer is that this customer is eligible for the refund, and the calculation also is done. Every time you are running this code with other type of the questions, you just put it in the code within query value. When you are running it, you can see reflection of it is inside of this output markdown to see what's going on and which tools are called. That's it for the MCP and tool call. The third approach is about model verification or self-checking. The idea is quite simple and different than previous approaches I already addressed. In this approach, we are not changing any pattern. We just rely on the output of the model that is generated. but we add another passover step here. The passover step can be done by the same model or another model. They're just checking again the content that is generated. And checking can be like checking the gaps or any contradiction of information or any misalignment with the provided context, any uncertainty in the output. All of this can be checked and as a feedback will be given to the model. Then the step of revision will happen. Either you can revise the output with the same model or you just raise it as a flag for human review. It depends on the risk tolerance you have in your own system. It cannot perfectly reduce the hallucination. Still, the models can miss part of the errors, but it can drop the hallucinations significantly because you're just adding another quality control layer on top. In some cases that you cannot completely mitigate the hallucination, but downgrading or mitigating hallucination would be a good filtration approach for you, then you need to think of this in your implementation. The reviewer as another layer will just go through pass over content, check about missing citations, inconsistencies, contradictions or misalignments of the content and try to give feedback to the model. That's just a simple logic. In previous video, we look inside of the MCP and tool use that help you to mitigate hallucination. The second approach is about model verification, which is exactly this practical example. We're going to go through it together. For this code, the same as previous one, I added the list of required Python libraries you need to install. The code is also simple. There is just one page of code, model verification self-check.py, that at the end the output of it also will go to output.markdown that you can see what's going on in the backside of the running. The logic of the code is quite simple. We will give the LLM model the first prompt. Here I name it draft system prompt. I mentioned to the LLM model that you are a helpful assistant and you're going to answer any question come from the user based on the context. If the context is missing, clearly say that there is uncertainty and ask for more information. And do not invert any citation, name, number, or policy detail. When this prompt is given to the LLM model with the input or query from the user, I would say, then you get something as output. That generated output will be given again to the model, but this time with the second prompt, which is about verification, verify system prompt. Now this time I give the verification role to LLM model. Inside of this prompt mentioned that you are a strict verifier for model hallucination mitigation. There are list of the checklists that you need to pass. For instance, does the answer, which is as an input will be given to the model, matches the user query question or not? Is every type of factual claim supported by provided context or not? Is there any contradiction, logical gap, or overconfident claims? And is there uncertainty stated where evidence is missing or not? All of these checkpoints are happening in the second run, and the output would be in the JSON format, that whether verification is passed or not, what is the risk level, what were the issues that are observed, and at the end put the output in the revised answer and with the rationale behind of this logic that you change the revised answer. But what is the rule to generate this output? I mentioned it here. If the answer is quiet, safe, and accurate, keep the revised answer similar to the original output that you got as the input. If the claims are not supported, remove the parts that are unqualified and then revise the answer, put it in revised answer. And never add facts that are not present inside of the context. If I go to the code, beside of this, I have to mention, assuming we have the application, that the user just asks about the policies of application. Policies about refund, security, and SLA. Let's go down now to the main function. Well, inside of this main function, it will at first check whether there is any open AI model available with the KPIs or not. So as I mentioned, I'm using GPT-5 mini. Then it will go through asking the user to enter their queries and then run the output. Let's run together and see how it goes. So it asks me for any input. I put this sample of question. What does the security policy says about encryption and log retention? And enter. Well, it created the output for us here. That what is the draft answer, first round of the running. This first round of the running is happening in the code. Easily you can see that the context is about the policies that are on top with the question of the user will be given to LLM model and first draft will be generated or first output. Then this first output will not be given as an output to the user, but it goes through verification by the model itself. So this output will be again given to the model with this verify and revise function to see whether the verification checklists are passed or not. And then when this function is running, we would have verification step that at the end it would come with this JSON format, whether the verification is passing or not, and at the end the risk level is low, the output was secure, so it would put the same or similar output inside of the revised answer with the rationale that it has behind of it. And at the end we would have the final answer, which is also in the revised answer. It got it from the code. If you want to also get how the logic is working, simply there is a output marked on file that you can see it here. Every time you run it, there would be overwritten of this file, but it's just for the sake of showing you how is it working. Just now I run the code with the model that I had, the question that I asked, and the type of the context that was used, which was about the policies of the security, refund, and SLA. But how is it working in the backside? You can see here that it's easily explained to you. The first part is about generating initial answer based on the query of the user and context, which is the policies. Then we will give this draft, pass it for second pass, which is about verification, and we would have final answer in the revised answer of JSON output. They are also explained in the next steps, and at the end we have final answer here. Well, quite simple but helpful for the case that you want to mitigate the hallucination and remove any unreliable output from your application. So to wrap up, I addressed 3 approaches to help you mitigate hallucination in your systems. The first one, retrieval augmented generation or RAG. RAG relies on external information to retrieve relevant grounded information for your system and then answer any type of question properly. The second one is about tool use and protocols such as MCP that standardize the logic of, okay, I don't know the answer, which tools I should call, when, and how to integrate back their outputs to the conversation. The third approach is more about model verification and self-checking. It's just another pass-over layer for quality control to check if there is any inconsistency, contradiction, or gap and give it as a feedback for revision. What if I have told you that the biggest mistake in large language model is not the model itself, but trusting the model too much? Even the most advanced large language models hallucinate, misinterpret the instruction, misunderstood the context, and sometimes generate unsafe or non-compliant output. If you're building large language model system, it's not even just inconvenient, but also dangerous. And that's why we're going to talk about one of the most important topics in large language domain, which is human in the loop or HITL. This is also an important concept in case of quality assurance. If you want your LLM-based application to be accurate, safe, and trustworthy, you cannot skip this topic. Let's break it down together. The first question is that what is human in the loop? Human in the loop is an AI workflow in which human can intervene or collaborate at key decision points to guide, correct, validate, or even override the model output. In LLM-based applications, it means human review of model output, human feedback to improve the output, human approval or rejection of action, human labeling for training or evaluation, and human intervention in the case that LLM model is uncertain or risky. Literally, HITL or human in the loop transform large language models from autonomous generator to collaborative assistant. In this case, the model proposes and human disposes. Now you may face the question that why HITL or human in the loop matters. Great question. If you have worked with large language models for any amount of time, you probably know the truth that large language models are super powerful, but they are not perfectly reliable. Well, they hallucinate, they misunderstood the context, they misinterpret the instruction, and even sometimes they generate the outputs that are unsafe or non-compliant. And as organizations adopt large language models in their real-world application, you cannot ignore the fact that these models cannot be trusted fully, and you need a system around it. And in this case, where human in the loop can come to the scene. HITL is not a backup plan, it's just the philosophy of the design, that you blend the human judgment with machinery intelligence to build the systems that are safe, trustworthy, and accurate at the same time. Now we are facing the most important question of this video, which is that why HITL is essential for LLM-based applications. Really good question, and we're going through 5 benefits of it one by one together. The first benefit, HITL ensures accuracy in high-stake domains. What I mean by that? Large language models can generate fluent and confident output even when they are completely wrong. And imagine in high-stake domains such as finance, healthcare, legal work, scientific research, enterprise decision-making, any type of the error can have serious consequences. And that's why HITL should be there to catch such errors before any serious consequences happen. The second benefit of HITL. HITL can reduce hallucination. Even if you are implementing the best RAG systems, it can happen that your RAG system retrieve irrelevant or incomplete documents. And large language models, any type you are using, it can happen they happily fill this gap and come up with the fabricated output. That's why HITL should be there to review the retrieved documents, to validate the reasoning of your model, and prevent hallucination before anything reaches your end user. And this approach actually dramatically improves the reliability of your system. The second benefit is covered. Now to the third benefit, which is HITL can bring safety and compliance to your system. What I mean by that? It can happen that large language models generate unintentionally harmful content, biased language, sensitive confidential information, or even policy violation. And HITL should be there in your system to be sure any legal requirements, ethical standards, and company policy are met very well. And this is really essential for highly regulated industries to bring HITL for their systems. The fourth benefit, HITL improves your user trust. What I mean by that, the users trust the systems that the human is there to oversee the critical decision making. And HITL in your system can bring transparency and accountability that, as a result, bring trust to your user. And the fifth benefit is that HITL enable continuous improvement. It can happen in LLM-based applications. You prefer to improve your application by fine-tuning, bringing the reinforcement learning, or even optimize your prompt, or even make better version of your evaluation dataset. And HITL there can be really helpful to bring such continuous improvement loop to your system. Well, we are at the end of the video. I hope you enjoyed the valuable content I share with you about human in the loop. For those ones who are following my work, you know that I design a roadmap to help you master LLM-based applications. This roadmap is designed for 2026. Since beginning of the year, I started sharing the content with you, and we are now in the fourth stage about quality and reliability. In this video, I'm gonna talk about one of the important topics of building a reliable production-grade LLM application. The topic is structured output enforcement. Before we start it, I have to clearly mention that the content of this video is just a piece of the full content that I'm sharing with my community. If you would like to have full access to the whole valuable content for free on the weekly newsletter basis, join my community. Everything is waiting for you there. Now let's get into this. The first question is that what is a structured output enforcement? Well, large language models are super powerful tools, but the case is that the core of these models is probabilistic text generator. You may not familiar with this core. I made a video way earlier about the topic of how LLMs work. Go back there and catch it up. And now back to the topic of this video. This core of the probabilistic text generator of large language models can be problematic for some of the applications. In some applications, we don't want that the large language model gets what we meant, come with creativity or improvisation. And that's exactly why structured output enforcement becomes super important. Some of the software pipelines, they need deterministic, machine readable, and structured output. Literally, structured enforcement is the kind of principle or discipline that you are enforcing the LLM model to produce a strictly formatted and compliant schema output. For instance, strictly following a JSON format or any other format that is machine readable you would like to set for your own application. Or even strictly giving the arguments of the function, or even constraint in case of the grammar. And with this type of the output that you are enforcing, you are sure that the downstream systems, they don't work with the surprise, they don't work with hallucination and ambiguity, because they can easily parse the output. Let's make it more tangible. For instance, imagine you are working with a large language model and you want to plan a trip. You ask the large language model to give you a task or create a task for you. The output would be, sure, this is the task for you. Go and book the flight for 10th of June 2026. Well, maybe that's perfect for the chat, but that's not the case for machine. It's quite useless. We would like the output like a JSON format that it would have two key points. One of them is the title of the task with the value of the flight booking. And the second key is about the date that has the value of 10th of June 2026. This is the format that is structured, predictable, and machine readable. Now the question is that why structured output enforcement is that important. It matters because large language models are hallucinating, they are improvising, they're adding commentary, and even they are breaking the format. Without a structured output enforcement, you are risking the system because the LLM model can break the format, which is challenging for downstream systems to parse the output, and even they fail. Even the large language models come with hallucinated values that corrupt the data. They may miss some of the fields that make your workflow incomplete. Even they would bring unexpected fields that brittle the integration, and even they can have inconsistent format that is impossible to debug. Literally all these together can make the whole pipeline to break. But with the structure output enforcement, you have the system that is quite predictable. The hallucination is reduced. You would have safe tool use. You can use the large language models as a deterministic, reliable output, and everything automation going quite smooth. That's why structure output enforcement is important. Now the question is that we got the point that the structure enforcement is really important, but when we should use it. Great question, and the simple answer is that if there is any machine in your system that has to read the output, then enforce the structure. But if there is a human at the end that read the output, then you just need to add flexibility. Let's make it more practical. For instance, if there are some downstream systems that they have to read the output of your LLM model like in JSON format, for sure enforce the structure. Or if you have some databases and you need to pass some of the queries of SQL to those databases, or even you have some tools that you need to call them with the API arguments, again you need to enforce the structure. In some cases that you would like have to deterministic workflows, or even there are some of the logs in the system that should be machine readable, again you need to enforce the structure. But you can add flexibility to other type of the applications. For instance, just using the LLMs for creativity, writing assistant, or conversational applications. In these cases, there is no need for structure enforcement. Now let's go through some of the techniques to help you with the structure enforcement. The first one is about JSON schema enforcement. JSON format is the list of the fields with their own allowed values, their data types with their constraint and nested structure. And you would like that the LLM produce the output based on the schema you are providing. It is really valuable to generate this kind of the schema of JSON in your output because you would reduce the hallucination, you would have quite consistent structure, and at the end it helps you to validate quite easily. You can use kind of prompt patterns to just enforce it. You can say, for instance, to the LLM, just produce the output with the schema of X that I have in mind. Or just follow the schema of X, or do not add any explanation. Any type of the word that you are strictly saying what you want. But it's not perfect, because still the LLMs can break the schema pattern. Even more complex structure in the JSON format can increase the failure rate, and at the end you would have other post-generation validation steps. That's why the other three techniques would come to the scene to help you out. Well, you already got to know how to enforce the structure output for your LLM model when you're passing any query to it. This is the first example we're going to go through together using the approach of JSON schema enforcement. The required Python libraries are mentioned in the required txt file that you can install it. If you want to know more about how the logic of the code is, you can also easily read the readme file. The output of the running also at the end would come to the output markdown file that show you exactly what's going on in the backside of the code. And how is the logic that we're going through it together? any type of the query from the user is coming, it will ask at first inside of the scope it is or not, then label it whether it is inside of a scope or not. We also pass the context when we are passing the query to the LLM model, that anytime it finds the answer, it will also attach the sources to this one for the case of the reducing hallucination and mentioning what resource or source is used here. We have system prompt. System prompt is for the case of controlling the output of the LLM model. Inside of this system prompt, I mentioned that the LLM model should follow a specific JSON format. And what is the format? This is the output schema I expect that the LLM model give the output. So I don't accept any type of the text, but put them all in the structured way as it is here. And if the query raise any task, what kind of task it is for my LLM application, it will be defined within this range of the values that I have. If it is checking the status of the query, whether we can support that specific query from the user or not in our application, or there is not sufficient context, or there is conflict with what we have, or it's out of the scope. So you can see I'm preparing the list of the possible options for LLM model, but no any other option around. Or what is the confidence that it can be supported, the status or not, with low, medium and high. And for the case of if it's gonna give any priority to the query comes from the user side, it would be priority 1 to 5. And if it's gonna route it to specific teams, then it will route it to different type of the teams that we have, or it cannot recognize which team should be routed to the query of the user. And if it can find it from the context, bringing those sources inside of this citation with this pattern of the SRC that we already put it inside of the code on top with the SRC pattern dash specific numbers. And any action should happen at the end is that the actions at first should come with the steps of ACT and the numbers and the description and rationale of those actions, if the LLM recognizes that for that query any action should be done. It is also checking some of the other cases in case of the compliance or not, so these are not really required in the case of your application for now. I don't need to explain it in the case that we just want to go through simple explanation how it is working, but later if you want to check the compliance level of your model and if it is any missing context and how you can handle it and other extra checking, you can just easily put it there. So that's the schema that I'm referring to, and I'm asking LLM model to follow this schema as it is. And any requirement, any query is coming from the user side, it should pass this specific schema as I mentioned. So I'm trying to go to main function. So in the main function, it will ask you to insert your query, and when you insert your query, it will check also the model that we are using. And when the API of the LLM model is also cached, then it will call the model with the question of the user, with the model name we have, and the context with those SRC lists that I showed you earlier, give it to the LLM model. So if I just show you this function, it will craft the user prompt, that the list of the questions, the guidance that define whether the query of the user is inside of a scope or out of the scope of the application. The context would be those lists of the sources, and also again it would add the instruction to recognize whether the input from the user is inside of a scope or not. But that's not the only case that we give it as the prompt to the model, but also we want the response format would be the JSON schema with the format that we wish. That's exactly the JSON enforcement that is happening in our code. So when the model is called and we ask for it to follow a specific schema, we have the output from the model. If it failed to call the model, it will go to the fallback, and again in the fallback model, the same logic of this model call a schema and then enforce the schema. So there is no other way around that the LLM model find any hole to generate its own random text. It should follow specific schema, we enforce it. At the end we have the output of the LLM model, and then we validate the output of the LLM model, whether it is following the same schema that we have or not. Also semantically we check the schema of the model. Semantically is more about the scope of the model. So if I just show you how is it working, the validation of the payload, we give the schema that we have and with the payload, and simply we ask for validation from the JSON schema Python library. It will check the schema is validated or not. In case of the semantically case, it will extract the citations to see if there is citation extracted or not. If in case of insufficient context is there and the confidence is low, then add some of the more explanation to the issues of the model, because it wanna try to find out what are the issues out of any gaps it finds in the output of the model. And after all of those issues are tracked in different conditions, then here when the semantic validation is done and all of the issues are recommended, then what is happening, if any of the schema or semantic is not okay, it will go through the repair. And what does it mean? It calls the function of the repair payload. It will pass all of the repair issues and also the response of the model to the LLM model and ask for it to again follow the same schema. And when again it will validate both the schema syntax and also the semantic of it to be sure that the schema and also the semantic, they are all okay. And at the end it generates the output and put it in the report for us in the file of output markdown that I already mentioned. So let's run it together to see how is it working. So it should ask a query from me. I have a question here that I'm simply copy pasting. Okay. I'm asking a question quite relevant to the context that it has, and I would like to see what would be the output. The output is printed here. We can see it also in the schema output markdown. If I just scroll down, this is just the scope classification that I already explained. My question, what is the question, and the context that we pass to the model. The JSON format output, you can see the first payload, that how it is following the structure. If there is any citation, it will extract it, what is the priority of it, it will recognize, and then if any action is needed, it will come as a ACT specific format that I ask for it. Step by step it will come, and other format that I need the LLM model to pass it. And in the case of the validation, I see that the schema validation is done. In case of semantic is also done, and it doesn't need repair at all. So simply the final output is the same JSON output I got from the first payload. It can happen that it may need a repair, but because we already enforce it very well, then in very few cases it would happen it needs repair, but that's for, again, assurance and quality check to be sure it follows the same pattern. Well, that's it. You could easily see that we enforced the structure output from LLM model without any random text output. Well, the second example that we are going through together is function calling enforcement, which is the enforcement of using specific functions with the JSON schema format that I explained earlier. In this code, the output will be written inside of this output markdown that you can easily see how is it going on in the backside. The system prompt is quite easy how to control the behavior of the LLM model. We say to the LLM model that you are a tool use assistant and do not respond anything with the form of the text, because we just want to call provided functions, not any other random type of the text. Let's go through it to clarify how is it working. Assume that we have a list of the tools in our application. One of them is about creating a task. One of them is about asking about the policies, documents that we have, or calculating arithmetic kind of operations. For all of these tools that are defined as function and they have a specific name, we want also they follow a specific pattern for a schema. Like for creating task, it's quite clear that we need the title of the task for a specific date, the priority of it, they are at least required. For the case of the policy, we need to know what is the section of the policy, in which domain, refund, security, SLA, which section actually the user wants question about the policy. In case of the calculation, we want to be sure that the expression at least saying one request in natural language type of the question. So each of these type of the tools, they have their own enforced schema, and we pass it to LLM model to just say what type of tool we should call. Maybe they are not really sophisticated. You can make it in better version when you are implementing for your own application. This sample is just for the case of helping you, giving you the insight how the design of the function calling should be. I also put some sample of the queries here that you can choose these ones and run it by yourself. For instance, we're gonna ask the LLM model to create a high priority task for us to book flight on a specific date, and later we can run the other codes. How is it working? Let's go through the main function together. It will ask for user query, it will check the model, that's which model I put, and the API credential. When all is done, then the system prompt query, the question of the user, besides of those tools that I showed you in the format of the dictionary, will be given to the LLM model. And the tool choose is for sure required. The output of the model would be the list of the tool calls. If there is no any tool call, it can literally give the output to the user that no model didn't call any function. But if there is any actually tool call, it will come through here and get the arguments or values that should be given to the tool. They are inside of the tool argument. The name of the function or the tool that also the LLM model recommend we should go for it is also the tool name. Both the tool name and arguments will be given to validate argument for validation. And when the validation is completely done, validation is about the schema and other type of checkpoints that I'm not going to the detail of it. When it is done, then it simply just run the specific tool that we need to call it with the arguments we're gonna send to the specific tool or function, and at the end we would have the result of it. And when we are running, the output will be written in the specific markdown file I already mentioned to you. Let's go through it together, and I will use the already first question listed in the sample here. Okay, I'm asking a high priority task to book flight on 10th of June 2026. It generated the output for us here, but I will go to the markdown file that we check together what happened. You can see I asked to create a high priority task for us on a specific time. So it already recognized what are the available functions and which function actually it called. In the JSON format output of the LLM model, you can see here that the type of function create task is recognized, and it could split different values for JSON schema. For title, it recognized the book flight. For date, it recognized the date and the priority high. So these are exactly the arguments with this schema that we ask for. They will go to the function of the create task. And you can see that this function is called. This JSON format is given as argument to the create task tool. For sure, the validation of the schema and argument should pass. Then we will go with the running of the function. And actually the function or the tool is executed, the task is created with this specific ID, title, date, and priority. So that's exactly how you can manage the natural language queries of the users to specific function calling and also the JSON schema enforcement. Let's actually run another sample here to see whether it's running correctly or not, or randomly I will go with this one. So if I run it again, we expect that it call the arithmetic function. Well, we will go again to output markdown file, going on top. I just ask about calculation of 49.99 multiplication by 1.15. Again, we have list of the functions. The output of the LLM model is that it could recognize the calculate function, we should call it. And what is the expression? This is exactly the arithmetic expression we should give it to calculate function. So that's the parsing part. That went very well. The validation also was correct. Then we are in the safe side to run this function and ask it to calculate this expression. And you can see the output that is here. Amazing, right? Hope you also enjoyed as well. Today we are diving into one of the overlooked but critical topics of building a reliable LLM application. It is called error handling and fallback strategies. LLM models, we know already that they are powerful, but they are not perfect. They may time out, they may malform the JSON format, they may hallucinate, and they may fail silently. In traditional software systems, the software developers would handle errors by throwing the exceptions, but we need structured reliability techniques to handle them in specific LLM applications. You may face the question that what do you mean? What is it error handling in LLM systems? Well, error handling in LLM system is a set of the techniques that help the model to detect the failure, recover from it gracefully, and keep the workflow stable. The failures can pop up in different formats. For instance, the LLM model throws back to you the JSON format which is malformed. It can hallucinate some of the values. It can miss some of the fields. It can face the retrieval error or tool call error. It can face refusal or safety block filters. It can timeout, and other cases can happen. For instance, the model can drift and you would have lower quality. For all of the type of the failures that the LLM models are facing, we expect these behaviors to happen because the nature of the LLM model is probabilistic. It means that they are just generating the next token or the next output or word. If you are not familiar with the nature of the LLM models, I already explained it in a stage 1 foundation. I would highly recommend you go to a stage 1 and cover it and come back here. But back to the topic of here, again, we expect different type of failures would happen in LLM applications. And effective error handling here can help you to be sure that the LLM application is still keep running when the model misbehaves. The second question is that why error handling matters. We already got the answer to some degree with the discussion we had so far, but to clarify it, without robust error handling, we make the system unstable. The random failure can break the workflow in your system easily. The outputs can widely vary and make your system unpredictable. Hallucinations slip through your system and make it unsafe. From the other side, when you put your system into the production, literally failures multiply under the load and make your system unstable and unscalable. And at the end, when the users watch over all of these issues, they lose their confidence and make your system untrustworthy. So you can see that without robust error handling, we face huge consequences at the end, and why the error handling is a core part of the reliability in your system, and it's not optional in production but mandatory. It separates literally your system from a flashy demo, MVP, COP, whatever you call it, to a quiet, trustworthy system in the production. You may face the question, okay, we got the point, it is important, but when we should use it? And the answer is that always put error handling in your system. And also it depends on the risk profile that you have. We highly recommend error handling in your system when specifically your LLM need to generate a structure output, it need to feed another system, it is part of the multi-step workflow, it is in direct contact with your system, even it needs to control over different APIs and tools, and it is non-negotiable if you cannot tolerate downtime, hallucination, and even the kind of unstructured output. Now let's go through some of the techniques that help you to handle errors. I will explain one of them in this video, and the two other cases are explained in my handbook. In this video, I'm going to talk about retries. It's quite simple and easy to implement. And the name clearly says retry or try again. How is the logic? You can, whenever face any failure or issue by calling your LLM model, then you use the same prompt you already used and retry it again with the same prompt. The second approach is that you can use stricter instructions in the second try. Or you can use validation feedback, and in validation feedback it gives the feedback back to the LLM model that a specific part of the output has issue and you need to fix that. So 3 cases specifically for retry, using the same prompt, using a stricter instruction, or validation feedback. We covered error handling and fallback strategies in this video, why they matter, and they should be the core part of the reliability layer in your LLM application. It is not optional, and for sure you need to consider them in your architecture before putting your hands into the coding. Hope you find it really helpful. Let's go through example, tangible one in the next video. Well, you got the point how to handle the errors, and one of the approaches that we are going through the error handling is retries. The people already coming from the background of the software engineering, data science, data analysis, they already may know that the retry is about multiple times trying to call the API and see what would be the output. That's exactly the same logic that we have here in this example. This example is also quite simple and easy to digest. We have multiple prompts. The simple prompt that we have is about system prompt, and we ask the LLM model to give us quiet structure output and only following the JSON format. Beside of this system prompt, we have user type of the request to the user, to the LLM model. The very base one is just giving the instruction that how the output of the LLM model should be, and there would be another version of it which is a stricter version of the user request, and it has more type of the rules and additional constraint on top of it. And why this is the case, maybe it can happen when you are calling LLM model, it's not following the rules that you already put it in the softer type of the prompt. That's why you can try it with the stricter one, and then with the hope that the output this time would follow all the requirements you want in the output. Now how is the logic is working? Let me go to the main function. Inside of the main function, the same as previous examples, it asks for your user query, check for the LLM model, check for the API, and then the request of the user with the context, which is about the list of the sources, will be given to LLM model with the maximum attempts of 3 times calling the LLM model. And it will call this function run retry pipeline. Inside of this function, it's quite simple. It goes with 3 level of strategies. The first one going with the softer type of the user prompt, then going with the stricter one, and at the end the validation feedback retry, and going through the loops of 3 times calling the LLM model. You can see here. So for each of the strategy, one by one, it will in each try, it will call one of the strategies on top, and then build a prompt using that specific strategy, softer one or stricter one or validation one, and then when it created the prompt, it will call the model and ask for the output. The output will be parsed in the JSON format. We would have a parse JSON object, and if any error is happening, also the error will be recorded. If there would be no error at the end and the JSON format, JSON object is created very well, then we define it as a success. And inside of our logs, we log 3 time attempts that we have by calling the LLM model and record the success. Anytime that we reach the success, we didn't face any error, and the JSON object is created from the output of the LLM model perfectly, then we can consider it as the final payload of the LLM model, and we break this loop to consider it. This is the satisfying level. We don't need to go to the next round of the retry, and then this output will be generated. If it is not successful, it will go to the stricter level of the prompt and the validation level. That's the level of adding more strict constraints to the prompt, with the hope that the output this time would follow the output exactly as you want. Then that's the logic. We can easily go through the sample. I listed sample of the queries here. For instance, I will just take one of them and run the query to see how would be the output. Well, let's see how is the output in the markdown output file. So this is the task that I asked the LLM model to do for me, or I would say the query of the user. And in the very first try, it recognized status as an insufficient context because it couldn't find any source. In the very first attempt, it used the very soft query, but it could recognize the JSON formats with the format that we asked for it, status, answer, and the citation is empty. But because the JSON format already was following and we didn't have the validation error, there were no error when we were extracting the JSON format from the raw output, the error also was 0, then the success was true. And since the very first run or first attempt we had successful output, then there were no need actually to go to the next runs. And that's exactly, we are satisfied with this one. But it can happen if you are asking any question and it fails with this extraction of the JSON object from the raw output, or it would have some errors in the case of validation that there is none of these specific keys that we are looking for it, then we would have something in the validation, then it was not successful and it will go with a more stricter prompt and try again to see with the hope of getting better result. That's it about error handling with the approach of the retries. Hope you enjoyed yourself by running the code by yourself. Well, we walked you through 4 disciplines of stage 4 of my roadmap: quality and reliability. The first discipline, hallucination mitigation, we covered 3 approaches out of 9 ones with hands-on experience. For the second discipline, which is human in the loop, we cover what it is and why it matters. For the third discipline, which is structure output enforcement, we covered 2 approaches out of 4 approaches, again with hands-on experience. And for the fourth discipline, which is error handling and fallback strategies, we cover 1 approach out of 3 approaches, again with hands-on experience. But that's exactly the surface that we cover so far, and my handbook has the complete full stack there, all approaches together with all scripts. If you would like your LLM application to be safe, predictable, and trustworthy, my handbook is where the value comes from. And this handbook is first part of the stage 4 quality and reliability of my roadmap. And there is another part that is covered in the next video and continues this journey. I also attach here the third stage of my roadmap, retrieval augmented generation, if you would like to cover this cool topic. Back again to this topic of stage 4 quality and reliability. Level up your reliability engineering of your LLM application, catch the handbook, and deepen your knowledge in the next video. Thanks for watching.
Grab the links to our practical handbooks in the description below to catch up fast. And make sure to subscribe to stay ahead.